Max, just a reminder to turn on your video, please. Okay, so we're looking at the ungraded copy of test 4 presently, and I was going through the coordination chemistry compounds. Coordination chemistry. No. Well, Max, I told you to let me know if there was going to be a problem with video. You know, that's something I said at the beginning of the course. You know, it's not like you're special or anything. Everybody has to put their video on. If you can't put your video on, then you tell me. And that goes for the rest of you as well. Anna. That goes for you too. All right, so we were looking at problem 27. I'm going to do one more of those examples. So a metal has an atomic number of 24. So what that means is it's going to be Ar 4s2 3d4. So you can see that this is going to match here. It's actually chromium, but that doesn't really matter here. And its charge is +3, which means it's going to lose 3 electrons. Now remember, the 4s electrons are the first ones to go. So after it's +3, it's going to be Ar 3d3. So the answer there would be 3. All right, does anybody have any questions about number 27? Okay, any questions about number 27? Okay, 5, 4, 3, 2, 1. All right. Okay. Number 28. A complex with the following formula possesses which kind of isomerism? So let me give you a little bit of guidance on deciding what kind of isomerism you're going to have to deal with here. Now, you kind of get off a bit easy here, because if I was giving this as a pen and paper test, you'd actually have to draw an appropriate isomer. So, and here I'm just looking for the kinds of isomers that you can actually get possibly with this. So the way that I would look at it is I kind of handle it like a flow chart. The first thing I would do is I would ask the question, is anion exchange possible? And anion exchange is possible if there's an anion on the outside and an anion as one of the ligands. We'll say different. Anion as ligand. So that would be possible, and if it is, then that's what you should do, right? So yes, then do anion exchange as a possibility. So an example that required anion exchange, or could have used that anion exchange, was this one. Because you've got Br negative here, and we've got Cn minus here. So that would have been a possibility. In this instance, you could, yeah, I know that you're going to have different letters here, A to F. The anion exchange is still possible as long as there's a anion on the outside, and then you can assume that one of A to F here is going to be a negative charge that could be exchanged. So that would be how I'd handle that. So if that's not the case, then the next thing I would look into would be stereoisomerism. And what you're looking for there is tetrahedral, which means 4 groups attached, all different groups. So different letters, obviously, is what I'm saying, A, B, C, D. Or octahedral, with En as a ligand. Okay, so we talked about that as well, or octahedral with En. So those are the 2 possibilities there. If the answer is yes, obviously it's going to be stereoisomerism.
I have a question.
Mm-hmm.
Would stereoisomerism be stereochemistry?
Yeah, it's the same thing. Yeah.
Oh.
Okay, stereochemistry. Okay. Okay. And if it's not, then the only thing left would be positional. So that would have to, that's the only thing that would be left over. And it would have to be one of those 3, really. I mean, to have none of these would be pretty unlikely. All right, so for this one, since it's got a cation out the front, so anion exchange is not going to be possible. I know that's a cation because it's a K, it's K plus. So that's not going to work. The other thing is that it doesn't have, well, it does have, it's not tetrahedral, but it is octahedral, and it's got 3 ENs on it. The reason I know it's octahedral is because En is a bidentate ligand, which means it's got 2 points of attachment. 3 times 2 is 6. So I know it's octahedral and it has En. So stereochemistry is definitely going to be possible as a form of isomerism for this one. Does anybody have any questions? All right, let me give you a couple of examples here of, see, I showed you one for anion exchange. I'll show you another one for stereochemistry, and that would be something like this. M, A, B, C, D, and then a K out the front. That would be an example of stereoisomerism, tetrahedral, all different groups. I know it's tetrahedral because there's 4 different groups here, 4 groups total. And positional, an example would be K, M, A to B4. That would be something like that. That's an octahedral, and the A2 could be 90 degrees or 180 degrees apart. So that would be positional. You'll notice it doesn't fall into either of the other 2 categories. All right, does anybody have any questions about stereoisomerism here? Or sorry, no, isomerism in general, I should say. All right, how do you feel about the isomerism here?
Octahedral is 6, right?
That's right.
So, just like to clarify,
Okay.
it wouldn't be, so if there is more than 4 or more than 6, it wouldn't be stereo.
Well, it never will be more than 4 or more than 6. It'll be either 6 or 4. It won't be, there's no, I'm not going to give you any other possibilities.
Okay.
All right, 5, 4, 3, 2, 1. Okay. So any other questions about this one? About the isomerism? Okay. An octahedral complex is determined to be strong field type. Now, octahedral, I give you the, whoops. It is KJ. The next thing we're talking about is the octahedral complex, determined to be strong field. And it's asking how, and it's determined the metal has 6 electrons. How many unpaired electrons does the metal possess? This is not actually a very difficult problem because I give you the splitting diagrams up here. Now, if it's octahedral, then this is the splitting diagram you're going to use. I make this section very easy here for you. Now it says that, so we've got a strong field. What that means is that this delta is large. This difference in energy is large because it says a strong field in the problem. It says there's 6. So what we do to fill the electrons is we go 1, 2, 3, 4, 5, 6. And that would mean that there are 0 unpaired electrons in that instance. If it was weak field, then I'm not going to put the designations on here. I'm just going to show you what it would look like if it says it's a weak field. It means that this delta is small. And that would mean that we do 1, 2, 3, 4, 5, and then the 6th one would go down the bottom here, and that would be 4 unpaired electrons. Okay, any questions? Any questions?
Okay. Which one has the high spin complex?
The high spin is the one with the greater number of unpaired electrons.
Okay.
Yeah. So the high spin is usually the weak field in general. A tetrahedral complex is determined to be of the strong field type. The metal has 7 electrons. Okay, so let's take a look. Tetrahedral. Tetrahedral, as you can see up here, is the one with 3 on top and 2 on the bottom. So you just have to choose the right one. I don't make it very difficult for you. I really don't. X, Y, X, Z, Y, Z. And it's got 7 electrons and it's a strong field type. So what that means is we've got a large difference in the deltas here. So I have to do the ones down the bottom first. So that's 4 and then 5, 6 and 7. So it turns out, I think for this one, it actually wouldn't matter if it was strong or weak field, to be honest, but it would end up being 3 unpaired electrons. And then once you put all the electrons in, this is the result you'd have at the end anyway. But the answer there would be 3 ampere. All right, let's see how people feel about those two problems. So we're talking about problems 29 and 30. How do you feel about problems 29 and 30 that have to do with unpaired electrons? 5, 4, 3, 2, 1. Does anybody have any questions? One person halfway understood. So any questions? Okay. Well, so that's all the coordination chemistry, crystal field theory type questions that you're going to see on the test. Does anybody have any other questions about the coordination chemistry section? Does anybody have any questions about the coordination chemistry section? Okay. All right, anything about the test in general here? Anything about the test in general? Yes, it's due Tuesday. I'm going to create a new question here. Give me a second. So just looking for a rounded answer here. And an honest one because it is anonymous. Okay. So looking for an honest answer to this question here. I don't know who's answering what. So. I'd like everybody to answer, please. Just one more. All right, that's good to know that you've all done something, which is good. I like that. But you'll have to do a lot more, just to make sure. I'd say probably for this one, I don't think test 4 is that hard. I'd say, I don't know, maybe 4 or 5 hours would probably do it. I would spend a lot of time doing the test. Is what I would do, the ungraded practice test. And I would be repeating the problems that you were having an issue with. I mean, the radiation stuff is pretty easy. And this crystal field theory stuff, the way I put the questions, they're pretty easy as well, I think. The only thing that you might have to work on a bit more is the concentration and colligative properties, which many of you have already seen before anyway. Because I know some of you took 2045 with me, so I know we did it there. Exactly the same thing, really. For those of you who didn't take 2045 with me, you probably did it already, or at least some of it in some other class. So I don't see that as being that much of an issue either. So I don't know. I feel like this is not that bad a test. So I think it's easier, much easier than tests 1, 2, or 3. So I think it's a bit of a gift, to be honest. Don't forget about the essay questions and the units quiz that goes along with this as well. Both of those are going to be due on Tuesday too. I've already got some essay questions, which is good, but I think putting them in earlier is always better than later. Does anybody have any questions? Okay. Yes,
The
Alexis.
last question on the units quiz, like, I don't know if, like, there's only 3 options, and then when you repeat them, it, like, marks it wrong no matter what you put. I mean, I could just be doing it wrong, but I think I'm doing it right.
Okay, I think what you're doing is, I will admit it, that one is a little tricky because it changes every time you take the test, and you're trying to figure out why it's changing, right?
Yeah, I guess, because
Yeah.
sometimes there's, like, 3 options, and sometimes there's 5
I
options for the last.
know. Oh gosh, I wonder why that is. Well, I can tell you, it's not a mistake with the quiz. I'll show you. I'll show you where the disconnect is coming into play here. Where is it? Units quiz down here. Let's see. So you're talking about this question down here, right?
Yeah.
All right. So the thing is that there's 3 possibilities for this question. It could be the KF question. It could be the partial vapor pressure question, or it could be about molarity. So it depends, and you have to look up here to see which one it actually is. It says change in freezing point delta TF, and that's got to do with the first one. So this would be the one that has the options you're looking for. If it was about partial vapor pressure, it would be saying that here somewhere in the problem. If it's about molarity and osmotic pressure, then it would say that about that one, and that would be the option you'd be using.
Oh,
Is that
okay.
is that clear?
Mm-hmm.
Okay. All right. Any other questions? All right. Any other questions about about the test, I guess?
How do you know when something is strong field versus weak field? Does the
Because
test...
I tell you.
Okay.
In
And
this
if you
instance,
were...
it's because I tell you. But if you were looking, it would have to be based on the list. Let me see if I can. I'm going to pull up the list for you in a second here. On the test, though, it's not something you have to be worried about because I tell you it's strong or weak field. But the answer to your question is that there's this list here, and anything on the left side of this greater than sign will be strong field, and anything on the other side is going to be weak field.
Okay. And is it like, does it take all of the ligands into account or just the highest ones?
No, it takes all of them.
Okay.
And if you had a mixture, you'd be the one that had more on that side, I guess. But it's unlikely you'd see a mixture anyway. Okay, any other questions? Any other questions? Okay. So I want to remind you that for the ungraded copy of test 4, before I go into it, you've got the practice test 4 videos here as well, which goes through every question and gives you a video for every single question there. So there's really not much doubt about how to do any of these problems. If you do run into hassles with the wording or how to interpret the problem, you can always just look at the video. The video will help you with that. That's not to say you won't have to practice it. You still will, but it won't be that big a deal. Okay, anything else before I'm just going to do maybe some of the concentration and colligative property problems with the rest of the time here, unless anybody else has a question that they want to ask here. Okay. No other questions? Okay. So you get 4 different kinds of concentration problems. The first one here is looking for a percent of X. So the percent of X here is going to be the mass of X. Now, I would expect you to remember this because it's just a percentage, and percents are always part divided by whole. So it's really no big mystery to it. In this instance, we're given 2 components, 15.00 grams of X and a density. That tells you it's a liquid, but that doesn't really matter here for this. And 690 grams of Y. So in this case, I don't even have to do any conversions from liquids to solids or anything. I can just do exactly what I'm doing here. 15.00 grams over 15.00 grams plus 690.00 grams. And that's times 100%. All right, does anybody
I
have
have a
any
question.
Yes. Mm-hmm.
So you said that this was a liquid, obviously, because it was density.
Mm-hmm.
If it was a solid, does this problem change at all?
No, not this one. No, the only one that changes is 18.
Okay.
Depending if it's a liquid or a solid. All the other ones, it makes absolutely no difference.
Okay.
Well, I shouldn't say
So
that.
just when you're looking for molality.
Molarity.
Oh yeah, sorry.
Because molarity is moles of X over liters of solution. And solution is both components, solvent and solute.
Thank you.
Molality is just moles of X over kilograms of Y. That's it. There's no X involved at all in the molality. On the bottom anyway, not on the bottom. All right. So 18, this is the one that does change depending upon whether it's a liquid or a solid. In this case, you know it's a liquid because you're given it in milliliters. You're also given a density as well. So that kind of helps you out here a bit. So for this one, you do need to find the mass of X first. So the way we would do that is 55.0 mils, 00 mils, and times the density. And that will give us grams. Now you might, well, how do you know whether to multiply or divide? Well, if you're looking for a mass, it's always multiplication. If you're looking for a volume, you're always dividing. But you can see here how the units will cancel. The mils will go away and you'll be left with just the grams. Okay, so that would be 47.552. I don't know if I'd be inclined too much to worry about the sig figs with these. because these are calculation problems, and generally speaking, you'll probably just keep all the significant figures until the very end, because that's the way that this thing actually does the calculations. So I'm not that worried about sig figs on these. What are we doing? That's right. So that's the grams. And then we need to convert that into moles. And we are given the molecular weight here, 98.00 grams. I get 0.4849. That's moles of X. Now the concentration or the molarity I should say, the molarity is going to be moles of X over liters of solution, which is really X plus Y, because X is a liquid. Now, if X was a solid, it would just be Y. And that's what I was talking about earlier.
You said if X was a solid, it would just be Y.
That's right.
Okay.
And the reason for that is because it's liters of solution. A solid doesn't change the volume very much, whereas a liquid does. That's why there's a distinction here. But the distinction only matters for this problem, number 18. That's it. It doesn't matter for any of the other problems. Okay, so let's talk about liters of solution here. So it's going to be, let's see, we've got 55.00 mils. And here we're given a gram of Y here. So I need to take that 880.00 grams. And that's going to be, I need a volume for that. So that'll be, I need the density, which is 1.19.
I just have a quick question. Where'd you get 55?
It's given in the problem.
Oh, I keep looking at 17. Never mind.
Okay. 1.19 grams and then 1.199 grams and then 1 mil on top here. So I'm essentially taking the mass and dividing by the density by flipping it like this. And that gives me a certain number of mils. Let's have a look at what that is. $733.9. 4 mils. So that's what goes in here as well. And that's times 1 liter over 1,000 mils.
So to find the milliliters of Y, you did 1 over the density.
That's right. If you look at
times the grams.
Yes, because if you look at how the units cancel, the grams cancel, and you're left with mils.
Okay.
But it all hinges on the density formula. Density is equal to mass divided by volume. Mass is equal to density times volume. Volume is equal to mass over density, which is the same as mass times 1 over density. Do you see what I'm saying? If you want a volume, you're going to have to take the mass and divide it by the density, which is the same as multiplying by its inverse or the flip of it. Does that make sense?
Yeah, that makes sense.
So that's the liters of solution. So as I said, it's moles of X divided by liters of solution. Now the moles of X is 0.4849 moles of X, and divide that by the liters of solution, which came out to be 0.78894 liters. And that'll give the answer that you want there. Does anybody have any questions about number 18? Okay. Number 19 is molality. Now molality, it doesn't matter whether it's a solid or a liquid. There's a for the solute. For 19, the molality is equal to the moles of X strictly divided by the kilograms of Y. You'll notice the X is not involved at all in the bottom of this one, and never will be. So moles of X, we already have grams here, so it's going to be moles of X is equal to 20.00 grams. Now keep in mind, you could have been given a liquid, which meant that you would have had to convert to a mass using the density formula, just like we did before. So that could happen. It doesn't happen here though. 1 mole of X, 81.00 grams is the molecular weight. Okay, so that's 0.2469. Now the kilograms of Y, let's see what we're given here. We're given milliliters of Y, so we need to convert that into grams. And we do that by multiplying by the density. As you can see, it's 0.994 grams per mil. So again, you'll see that to do that, that means we end up with grams. And that's a 61.6 grams. And then let's see, so we need to convert that into kilograms. So 1 times 1 kilogram over 1,000 grams. So that's 0.0616 kilograms. So we just substitute in the moles of X and the kilograms of Y. And there you go, that's it. Does anybody have any questions? For number 19? Okay. Number 20 is mole fraction. And you can see here, you're given milliliters of X, which means you need grams so you can get moles of it. Here you've got grams of Y, you just need to convert that into moles, and then you can calculate the mole fraction of X. Now the symbol for mole fraction is this Greek letter chi, which is moles of X over moles of X plus moles of Y. That's the formula for mole fraction. Again, it's kind of like a percentage, except it's a fraction because you're not multiplying by 100%. So 60.00 mils and we multiply it by the density. And that's 57.6 grams. and that's times 1 mole of X over the molecular weight, which is given to us here, 88.00 grams. And I get 0.654 moles of X. And we need to figure out the moles of Y here. We've already got the mass, so I don't have to do any conversions for that. And that's times 1 mole over the molecular weight. This is Y. And let's see, what's that? That's 75.00 grams. So 655 divided by 75. Okay, we get 8.73 moles. So then I just substitute those values in up here. So that's moles of X, this is moles of Y. And then that'll give me my answer there. Does anybody have any questions about number 20? All right, let's see how you feel about questions 16 through 20. Or is it 16 through 20? 17 through 20. How do you feel about 17 through 20? Ones we just did. How do you feel about them? 5, 4, 3, 2, 1. Well, that's really good news. I like that. Good. All right.
I just have a quick question.
Yes.
So, for like the 20 and 19, how it's like example for 20, you are given the milliliters of X. Will you always be given the milliliters of X? Or will you be given like grams of X?
That could be given either.
Okay.
And you have to work on the fly, but it's all about using that density. If you're given mils and you need grams, then you'll multiply, right? Let me take it back here. It all comes back to the density formula, which makes it a little bit easier to see. So the volume is equal to mass divided by density. So this is the story. If you have grams and you need mils, you'll divide mass divided by density. If you have grams, you have mils, you need grams, then you'll multiply and you'll do mass equals density times volume. So it all depends on what you need, and that's going to depend upon what you're looking for. Sometimes you need grams, sometimes you need mils. It's going to vary depending on the problem. And you could be given anything for anything here. You can be grams or mils for X or Y. That's why I think it's important to do this ungraded copy of the practice test a number of times so that you get to see all those different possibilities and work with them. Is that clear?
Yeah.
Okay.
Thank you.
No worries. Anybody have any other questions here? Okay. All right, so for this one, we're looking for freezing point of solution, and here we're given 40.00 mils of X and the mils of Y as well. Now what we're trying to do here is apply this formula, which is given to us here, delta TF is equal to KFM. You are given the value of KF in the just above here, so you don't have to, sorry, no, KF is down here, mole freezing constant, it's given to you. And then you're asked to find the freezing point of solution. So you do need to find the delta TF because you are given the pure freezing point here as well. So that's helpful. All right, does anybody have any questions so far? Okay. So our first mission is to find the molality. Now, molality is going to equal moles of X over kilograms of Y. So that's going to be my first mission, is to find the moles of X. Now, I do have the milliliters here. And the density is 1.244 grams per mil. So you see I'm multiplying the density here to get the mass. Cancel the mils. And then to get the moles, divided by the molecular weight, 78.00 grams. I mean, this just shouldn't be a matter of memorization. You should just be using the dimensional analysis to get the units. I think that's the mistake that a lot of people make. They try and memorize everything. It's not the idea. It's not what I'm trying to get you to do. What I get there is 0.6379 on the moles. Now I need kilograms of Y. And what I've got is a volume, so 855.00 mils. And again, to get the grams, I need to multiply the density. And then I also need to convert that into kilograms. Okay, I get 0.7549. And that's kilograms of Y. So the molality here, just substituting those values in, which is going to be 0.6379 moles divided by 0.7549 kilograms. And I get 0.845. And the delta TF then is going to be, see, KF 2.710 degrees Celsius per molal times the molality, which is 0.845. And that becomes 2.29 degrees Celsius. Now the new freezing point is going to be, let's see, so it's minus 12.00 is going to be that minus 2.29 because it's freezing point depression. So I get minus 14.29. All right, does anybody have any questions about number 21? Does anybody have any questions about number 21? Okay, number 22 is looking for the boiling point, and you'll do this pretty much exactly the same way, except that at the end, when you're getting the new boiling point, you won't subtract, you'll add. And the reason for that is because it's boiling point elevation. Does anybody have any questions about number 22? I'm not going to do number 22 because it's pretty much exactly the same except for that last part. All right, how do you feel about number 21 and 22? How do you feel about number 21 and 22? Five, four, three, two, one. Okay, that's good. Okay. I get the impression though, the very people who should be attending lecture aren't. You guys are attending, but there's a bunch of people who aren't attending who should be, I think. Okay, let's have a look at 23 and 24. Now you are given here the formula for this one. There you go. And it's the delta P solvent concentration solute times P naught of solvent. Now the concentration specifically is the mole fraction. So we're looking for the mole fraction of X here. Because that's the formula here. So chi X is equal to mole X over mole X plus mole Y. And you can see you're given both of these here, you're given milliliters. So this is for X. Times the density. $18.63.
I have a question.
Yeah.
Did we not need to divide it by its molecular weight?
You do. And actually, I should do that. I'll do that here. Thank you.
Okay. No problem.
I just didn't get to that. Times divided by 7. I probably would have at some point because I would have realized, oh, I need moles. Thanks. I get 0.251. 7, 2.18. Now for the Y, we got, let's see, we've got 690, same deal, 9.00 mils times the density. You'll notice I'm very good about the units because the units help me to know if I have to multiply or divide, so I can see how everything cancels. And then, yeah, we'll go ahead and just convert that straight into moles here. And what have we got? 62.00. 619 times 0.824 divided by 62. And I get 8.227. Now we can get the mole fraction of X. By just taking those and plugging them into the formula at the top there. And I get 0.0296, 0.029, and I'll make that 70. There's no unit on mole fraction. Now the formula is delta P of the solution is equal to the mole fraction of X times the P naught. And the P naught of the solution, the P naught is the pure vapor pressure. So it's 0.02970, and the pure vapor pressure we're told is 35.00 torr. That's in the problem. And that's 1.039 torr. Now to get the new vapor pressure, it's always vapor pressure lowering. So the new vapor pressure is going to be 35.00 torr, which was the pure, minus 1.039 torr. And that gives us our answer. All right, does anybody have any questions about that one? About number 23? Okay, let's see how you feel about number 23. Whoops, wrong one.
I have a question.
Yeah.
So you got the delta P solution by taking the equation that we just did times the pure vapor pressure, and then at the end to get the answer, you took the delta P and then you minus the pure vapor pressure.
That's right. Well, you minus it from the pure vapor pressure, yeah, because it's vapor pressure lowering.
All right.
How do you feel about this one, number 23? Five, four, three, two, one. Okay. Does anybody have any other questions about that one? Okay. Number 24 is going to be about osmotic pressure. Now, the formula you're given there, the osmotic pressure, is equal to mRT, which means we need the molarity. Now, the molarity is going to be moles of X. Now, in this case, we've got to see if X is a liquid or a solid. So looking at that, I can see that it's given in volume, so it's a liquid, which means that it's going to be volume of solution, which means it's volume of X plus Y in liters. Okay, so we've got our volume of X here, so that needs to be converted into grams. And that's times 1 mole over the molecular weight. And and this is for X. Okay, point
I have a
three.
question.
Yes.
So if you were given the grams of X when trying to find the moles of X, you would just divide it by the molecular weight.
You would. But the other thing you'd have to worry about here is if X was a liquid or a solid.
Yeah.
And if you weren't given a density, you'd have to assume it was a solid. But if it was a solid, I think I'd tell you it was a solid as well.
And if it's a solid, it would be moles of X divided by only volume of Y.
That is correct.
Okay.
Because solids don't really affect the volume. Okay, so there's your moles of X. Now we need the volumes. What have we got? All the volumes here, that's easy. It's going to be 840. So that'd be the volume of X plus Y in liters. It's going to be 800.00 mils plus 40.00 mils. And that's going to give us 0.84000 liters. And then the molarity then is going to be those two divided. So let's see. I get 0.448 on the molarity. And the mole fraction then would be just substituting into that, which would be 0.448 molar times 0.08. You are given this above, by the way. You have to remember it. Liters, atmospheres, per mole per Kelvin. And that's times the temperature. So 53 degrees Celsius, that needs to be converted into Kelvin. That'd be 326. Okay. And so multiplying all that out, and that will give you your answer. It's going to be 117 atmospheres. Okay. Anybody got any questions? Anybody got any questions? Okay. How do you feel about number 24? How do you feel about number 24? Five, four, three, two. Okay, good. Okay. Does anybody have any other questions about the test? I mean, I went over the hardest problems, I think, today. All right. Well, I'm inclined to leave it there unless anybody's got something else. If anybody wants to hang around and ask me anything, they're certainly welcome to. And I will see you all. Well, I guess I won't see you on Tuesday because there won't be a class on Tuesday because your test will be due. But anyway, best of luck. But work on it over the weekend. Don't wait till Tuesday. Okay. Good luck, everybody. I'll see you later. Have a good day. Thanks, Kate.